business owner, okay, and you are very business minded, and you have this tax response. So as a waiter, you would like to develop a model that will allow you to make a prediction about what amount of tip to expect for a given amount. Okay, so in a particular evening, you decide to collect data for 6 customers, okay? Now, you didn't collect data on the amount that the people spent on the food. You just collected the amount of tips that they gave. So basically, this is the data that you have, okay? So the question is, how might you predict the tip amount for future meals using only this data? All right, so you have 6 people who have come to the restaurant, okay? You didn't collect the data on the amount that they spent on the food, but you collected data on the tip that they gave, okay? So we have, 6 meals, everybody gave a tip. So you have the tip amount, okay? So for meal 1, that's $5, $17 for meal 2, 11, 8, 14, and so forth, all right? So basically, so what we're going to do in this instance is to calculate the mean, isn't it? Since we don't know, we don't have any other data, okay, in order to predict future tips, then we calculate the mean, then that will give us an idea of what future tips might be, okay? So if you are to plot this, you have various data points for the 6 meals, okay? And then we have the mean of $10, okay? Of course, I'm sure you all know how to calculate the mean. You add all the tip amount, and then you divide by the number of meals, okay? So on this graph, you will see that the mean is $10, all right? And then the data points for the tip amount have also been demonstrated here. So some of the tip amounts, some of them were below the mean, some of them were above the mean, okay? So if you take the first one, for instance, it was 5, isn't it? So the first meal, 5. So you see that it was below the mean of 10. If you take the second tip amount, that was 17, okay? So that goes just a little above 16, okay? So you see 17 here, that is so, you see that it's also above the mean. The next one is 11, which is also above the mean of 10. And then the fourth tip was 4. Sorry, the fourth tip was 8, okay, which is also below the mean, all right? And then the fifth one, 14, and then 5. Please, are we all okay with this for now? Are we all okay with this for now? Any issues with this, with the graph and also the data points and the mean? Any issues?
No, please.
All right, so yes. So with only one variable and no other information, the best prediction is to use the mean, okay, on the sample, okay? So in this case, we'll say that every variability within the amount can be explained by the tips that has been given. So here, you see that the difference between the mean and then the various data points can be shown, okay? So the first one, the mean was 10. So you see the first tip amount was 5. Therefore, it was way off by 5, okay? Less than 5, so that's -5, okay? The second tip was above the mean by 7. So here we have +7 and so forth, okay? These are what we call residuals, okay? These are what we call the residuals. So basically, it's the difference between the predicted amount, okay, and also the observed amount, All right. All right. So here we have, if we are using the mean as the predictor, that is 10. All right. And then the actual amount, that is 5, 17, 11, 8, 14, and 5. Okay, the differences for the residual. Okay. So we see that we have -5, positive 7, positive 1, -2, and so forth. Okay. Now, when you add all the residuals together, they should give you 0. Okay. When you add all the residuals together, because these are just way the differences between the observed and then the predicted. If you add all the residuals, and these residuals are also what we call, they are also errors. Okay, they are way off the how do you call it, the predicted amount. Okay, all right. So residuals should always add up to 0. So if you look at the ones at the top, we have positive 7 plus 1, that's 8 plus 4, that gives you 12. If you look at the ones that are below the mean, okay, -5, -2, -5, that also gives you -12. You add the 2, it gives you 0. Any question on this? Any question? Okay, let's. Now, when we square all this, remember we've done this before, but we didn't use the term sum of square errors. Yeah, I think we've used it when we were doing the. Okay, it's okay. I think when we're doing we're mapping the script plots. I mentioned something like that. Okay, so basically, when you square the residuals, okay, and then you add them up, okay, you square the residuals and then you add them up. That gives you the sum of squared errors. Okay, sum of squared errors. Right. Any question? Do you remember variances? Okay, when we're calculating standard deviation, we did a similar thing. Okay, we found the difference between the observed and then the predicted, and then we summed all of them up. And then when we wanted to find the standard deviation, we found the square root. Okay, it's a similar concept here. Okay, so we have the residuals, that is the errors. Okay, we square them up. Therefore, all the negatives become positive. When you find the summation of them, it gives you the sum of squared errors, which is 120. Okay. Any questions about the sum of squared errors, which is 120? Any questions about that? It's just the residual, okay? The errors, we square all of them and then we add them up. That gives us 120. Any questions on this one?
No, please.
So basically, is to find a model that minimizes the sum of square errors. Okay? So we want to find the model that minimizes the sum of square errors. So if a model gives a higher sum of square error, okay, we are pushing for the one that gives us lower sum of square error. In other words, we want a model that is able to predict better, because if the sum of square error is greater, that means that the errors are huge, isn't it? So you want to minimize the error, right? So the goal of simple linear regression is to create a linear model that minimizes the sum of squared error. Okay. Now, when it comes to simple regression, linear regression, okay, we have what we call the deterministic model. Okay, and then also the probabilistic model. So with the deterministic model, here there is no room for error. Okay, so you see the first plot. Okay, here the y is the dependent variable. Okay, then beta 1, okay, is the coefficient. Okay, and then we have the value of x. Okay, so here there is no room for error. Okay, however, when you compare that to the probabilistic model, okay, you see that all the points are not on the line of best fit. Okay, you see that diagonal line there. Some of the points are off the line. Okay, so that means that they are a bit off what has been predicted. So therefore, there is some kind of error. All right. So in this case, the equation for the probabilistic model will be if, let's say, the first one was 1.5x. Okay, and we'll explain all that, okay, later. Here we add the error term to it. Okay, so here it becomes y is equal to beta x plus the error. Okay, so with the probabilistic model, it makes room for error, whilst the deterministic model doesn't make room for error. And practically, you know that we cannot have a model that will predict perfectly. There will be room for error. Okay, so normally you will see that we will use a regression equation that makes room for error. Okay, so you will have something like this. Okay, so y is equal to beta 0, beta sub 0, and then beta sub 1 x plus e, okay, or the error term. So the first one is the intercept population. Okay, the B1 is the slope of the population parameter. Okay, and then the epsilon. Okay, here is the error term. Okay, that is unexplained variation. Y. Okay. So the one on the left, the equation on the left is when you are talking about the whole population parameter. Okay, the whole population parameter. So here the expected value of y is equal to b beta sub 0 and also beta sub 1x. Okay, so the expected value of y is the mean or expected value of y for a given value of x. All right. Yes, Delasi, is there a question? Delasi, your hand is raised up. Is there a question?
Yeah, I was not getting it. So maybe if you could go over when you are done with this part.
You mean the equation?
And even the previous slide, that was
Okay.
why I got.
This one?
Yes, please.
Okay, no problem.
The,
So
the
here,
one,
where? This one?
no. The one, yeah. So please, I was asking if why is me.
You are asking what the why? Can you be?
Why is the me?
Why? No. Here, we want to predict y. Okay, so we have x and then y. Y is kind of the dependent variable. Okay, and then the x is the independent variable. Don't worry, I will explain all that as we go along. Okay. So here we want, so this is just a simple linear regression graph where we want to predict y. Okay. So the y here is the dependent variable. So it depends upon the equation on the right. Is that okay? We've moved on from here where we were using this as the mean. We've moved on. So it's not really about the mean that we calculated here. Now we've moved on to determining the regression model. Okay.
Okay.
Okay. Okay. So basically, the expected value of y is the mean or expected value of y for a given value of x. Okay. So basically, if you want to find the expected value of y, it's just like a normal distribution where we have the value for the mean. Okay, so whenever you have something like this, okay, we want to determine the expected value of y given x. Okay, given x, and this can be put in a model, okay, in an equation like this. First of all, we need to understand that the expected value of y is made up of two components. We have the intercept and then we have the slope. Okay, the intercept is beta sub 0. Okay, so that is if there is nothing, if there is no other information on independent variables. Okay, we have something like how can I explain this? Okay, so let's say you have do you remember, for those of you who have postpaid meter, okay, if you've seen a particular bill for postpaid meter, or in the past when we used to have how do you call it? We used to have mobile phones that were on contract. Okay, I don't know whether you remember. Now most of the phones are prepaid. Okay, so we use the amount that you've used. But in the past, you have something. Okay, let me use the electricity. So electricity, let's say you are on postpaid meter. Okay, now whether you use electricity or don't use electricity, when your bill comes for the postpaid, there is a fixed element to it. Okay, there's a fixed amount to it. That is basically like your fixed cost. Okay, so that one is whether you use electricity or you don't use electricity, you pay that amount. Okay, and then when subsequently you use electricity, then the variable cost will come and add to your fixed cost. So you can liken this to, let's say you can liken this whole equation to, let's say total cost is equal to fixed cost plus variable cost. Okay, so where there is no variable cost and there is fixed cost, this is like your intercept. Okay, so this is your intercept. So it is the baseline where your slope starts. Okay, now when you use more electricity, then your variable cost depends upon how much electricity you've used will come and add to your fixed cost. So if you see the first plot on your left, okay, you see that the B sub 0, okay, is a horizontal. So it's a horizontal line. Okay, so if you compare it to the x-axis, no matter the value of x-axis, it stays the same. Okay, the B sub 0 stays the same value. Okay, now when you come to the second plot, okay, now you see that it begins to rise. Okay, so this is the slope of B1, but you can see that the B1 starts from the base of B0. So it adds to what you have in B0. Okay, all right. Now it can slope upwards or it can slope downwards. So when your slope is positive, it slopes upwards. Okay, and then when your beta is 0, okay, or your slope is negative, it slopes downwards. Now this is reflected in the equation. So if you have the expected value of y, okay? That is the intercept. So the first one, for instance, there is no slope, okay? It's just the intercept. Now, when you look at the second graph, all right? Here, there is the intercept plus b1x. Okay, so the b1x is the slope, or beta sub 1x is the slope. All right, okay? And here, you can see that the beta sub 1 is positive. Therefore, your slope faces upwards. Okay, where your slope goes downwards, okay, the beta sub 1x is negative. Any questions about the equations and then the slope of the regression model? Any equation? Any question about the equation? We'll go into the mechanics of how they are calculated, okay? But this is just something for you to understand how the slope works. Okay? Any questions about the intercept, the slope, the positive slope, and then the negative slope? Any questions about it? Any questions? Okay. Please feel free to stop me if you don't understand anything, okay? So basically, where we have the expected value of y, okay, that is the intercept, and then the coefficient, okay, that is in other words the slope. This is a situation whereby you are using the whole population parameter. Okay, so since most of the time you will not know the population parameter, and rather we use a sample, okay. So in this case, we rather estimate y, okay, instead of using the estimated value, the expected value of y, we use the estimated value. Okay, so we use y hat, okay, and then equal to p sub 0 plus p sub 1x. Okay, so let's put this into our example and then see if we can make much more sense of it. Okay, are we okay with this? Are we okay with the y hat and then b0 and then bx1? Are we okay with this so far?
Yes, sir.
Are we okay? Okay, good. Okay, so let's plug this into our previous example. Let's revisit our example and then put in more data and see if we can make sense of everything. So let's assume you are a small business owner on a very business-minded server, okay? All right. At a nice restaurant. So as a waiter, you would like to develop a model that will allow you to make prediction about what amount of tip to expect for a given amount. Therefore, one evening, you collect data for 6 meals. So this time around, you have data for the total bill that was spent and then the tip amount that was given. Okay? So the first person spent $34 on their meal. They gave a tip of $5. Somebody spent $108 on a meal, give a tip of $17. $64, give a tip of $11. $88, give a tip of $8, and so forth, up to $51 on a meal, and give a tip of $5. Okay. So we have this data now. So we want to know to what degree the tip amount can be predicted by the bill. Okay, so the tip amount here is the dependent variable, and then the bill is the independent variable. Okay, because we want to predict the tip amount. Okay, so the tip amount is depending on the bill that has been paid. Okay, so that is the model we want to predict. Okay, so therefore the total bill becomes the independent variable, and then the tip amount becomes the dependent variable. Please, any question about the dependent variable and the independent variable? Because knowing the difference between the two will make your work easier, especially when it comes to regression, so that you don't misinterpret the equation. So every time your y here is your dependent variable. So the y hat we have here is depending upon what is happening on the right. The ones that are happening, the variables that we have on the right are all independent. Okay, they are independent variables. Okay, but they all come together to affect what happens to y. So that is why y is the dependent variable, and then the others on the right are independent variables. Okay. So whenever you are given a question, you should be able to deduce from the question which are the dependent variables and then which are the independent variables. Okay, so the dependent variables normally will be the ones you want to predict. Okay, and they will depend upon something. Okay, so whatever is being dependent on, okay, are the independent variables. Okay, and why, and then the one you want to predict will be your dependent variable. Yeah. So basically, this is what you have. So this is the least square method. So I've told you already that this is, we want to minimize the sum of squared errors. Okay, so that is the goal of the least squares method for regression. All right. So let's plot this data on our scatter plot here. So here we are comparing our bill and then the tip amount. Okay. So the first one, the bill was, the tip amount was $5, and then the amount spent was 34. Okay. All right. So the next one was what did we spend? We gave a tip amount of so this one, most of them are scattered here. So the first one, okay, so let's see the first data point. So this relates to the tip amount of 5 and then 34. The second data point relates to the tip amount that was also 5. Okay. And then that was 51. Okay. All right. And then another tip amount of let's say the third data point, and the tip amount was it 11? Yes, 11. And then the amount spent was 64. Okay. So the other one, the tip amount was 8, and the amount spent was 88. The other one, tip amount 14, the amount spent was 99. Okay, and so forth. Okay. Any questions about the scatter plot? We've done a lot of scatter plots already. Are we okay with this?
Yes, Nana.
Okay, good. So we want to, so for us to calculate B1, okay, it comes with this, it comes in this form of calculation, okay. So we want to look at the independent variables. So we would have to look at the mean of the independent variable, and also for each of, so we will have one observation, okay, and then we deduct the mean of that variable, of the independent variable, okay, and then we'll take the dependent variable and also look at deduct the mean from each observation. We sum all of them up, Okay, so for both the independent variable and independent variable, we find the differences, okay, sum them up and then find the product of the two, okay, and then we divide by the sum of squared errors for the dependent variable, okay. So here the S bar is the mean of independent variable, okay. Then the XI is the value of independent variable, okay, whilst the Y bar is the mean of dependent variable, and the YI is the value of independent variable, the value of dependent variable. Okay, so that's just for the B1. Okay, that's just for the B1. So for the B sub 0, okay, for the B sub 0, it is the mean of Y minus the mean of the independent variable multiplied by B1. Okay. All right, so that's how we calculate the intercept. Okay, so the intercept, that is the B0, is equal to the mean of Y, that is the mean of a dependent variable, minus B1, okay? That is the coefficient, okay? Then multiply by the X, okay? X bar, that is the mean of the independent variable. So based upon this, you should 0 without first calculating B1, because within B0, there is B1, okay? B sub 1, okay? So every time you should calculate the slope first before you come on to calculate the intercept. Okay? Any questions about how this equation is? Yes, Delasi.
Please, my network went off at a point, so I missed you from
Hey,
the.
Delasi, your network. You can't be going back every time your network.
Oh no. Okay, sure.
So you don't know how far we've even gone.
Oh, I can tell.
Okay, so let me go back a bit. Is it, was it here?
Just this, please.
Okay. Felicia, yes, please go ahead.
Hello, sir.
Felicia, are you okay? Please go ahead. Are you asking a question?
I wanted to find out whether the slope as the slope of a line, a straight line. Hello.
Yes, Felicia, please go ahead.
Yes, so I'm asking whether the slope that we are calculating, is it the same thing as the slope of a line? A straight line, please.
Yes.
Okay.
Yes.
Thank you.
Okay. All right. So was that Felicia? Okay.
Yes,
so if I find also, then please put your hand down. Okay. All right. I'm sharing, so I can't see your names. Thank you. Okay, so Delasi, so we have our bill here. Remember when we started, it was only the tip amount. All right. But now we've got information about how much was spent on each meal. Okay. So we have the amount that was spent on the meal and also the tip amount. All right. Now remember we wanted to predict the tip amount based upon the amount that was spent. Okay. So in natural sense, the tip amount is your dependent variable. It depends upon the bill that was spent. So your X basically is your bill, and then your Y is your tip amount. All right. So normally your X is your independent variable, and then your Y is your dependent variable. Okay. So based upon this equation, okay, remember that we've established that the regression equation is B0, that is the slope, the intercept plus the slope. The slope is the B1. Okay, and then B1 is calculated by looking at the difference between the mean of the independent variable and then the value of independent variable. You look at all the differences and then sum them, okay? And then you come to the dependent variable, look at the differences between the mean and then individual values, and then you sum them. The two summations, you find the product of it, you multiply them. And then you divide by the sum of squared errors, okay? So for the dependent variable, okay? So that is xi minus s bar, and then you square them and then find the summation of it, all right? So I was making the point here that when you come to the calculation of the intercept, okay, it is the mean of y, that is the dependent variable, minus the slope, okay, b1 multiplied by the value of x. That's the mean of the independent variable, okay? But you see that for you to calculate the intercept, you need b1. Therefore, every time it is advisable to calculate b1 first. Then the value that you get for b1, you come and plug it in when you are calculating the intercept so that you'll be able to get the value for the intercept. Because without that, you can't calculate the intercept. Yes, yeah.
Sir, so from this formula, does it mean that the linear regression is the same as the mean of the dependent variable? Because
What do you mean by the mean of the dependent variable?
Okay, so within the formula for finding the linear regression, you said it's b0 plus b1 xi.
Yes.
And looking at the b0s here, it seems that we've moved the b1 x1 to the other side. Is that what you did? I'm talking of the formula up there.
This one, the y hat.
Yes.
Mm-hmm.
Yes. Is that the formula we are trying to use to find the b0s?
Okay, so for you to find a predictive value for y, okay, you need to find the intercept plus the b1 multiplied by a value for the independent variable, okay?
Yes.
So we are picking the components of these ones, okay? So for the b1, that's the formula you get on your right, okay? And then for the b sub 0, that's the formula you get on your left. Probably let's work this and then if we put it, we have some data and then we plug it in. Probably it might make more sense to you.
Okay.
Okay. All right. Yes, give him praise.
Nana, please, I wanted you to go over how to know the difference between the dependent and the independent variable.
Okay, so the dependent variable normally is the one we are trying to predict. Okay, and then the independent variable is what the predicted value will depend on. Okay, so let's say we want to determine, so based upon this model, we want to determine the amount of tip that can be given based upon the amount that was spent on food. Okay?
Okay.
All right, okay. So in this case, the amount that was spent on food is the independent variable. But the amount that will be spent on the tip will depend upon the amount that was spent on food. All right?
Yes, please.
So you need to know from the context which variable depends upon the other. So the one that depends upon the other becomes the dependent variable. And normally it is the one we are trying to predict. Is that okay? And then the other one is what the dependent variable kind of depends on. So if you want to let's say you want to predict transportation fare from Accra to Kumasi. Okay, you want to predict transportation fare from Accra to Kumasi, and it is based upon the distance that you travel. Okay, or it depends upon the amount of fuel that is used. In this case, the fuel becomes the independent variable, and then the amount that will be charged will become the dependent variable, because depending upon the fuel that is used. Does it make sense? So every case, you need to isolate which variable depends upon the other. All right. Hello, is it okay? I'm not getting through.
So we are okay.
Okay, who asked the question? Is it giving praise? Okay. Okay. All right, so yes, so we have this. So let's put this into real figures, and then probably we can make much more sense about what we've done. So remember that the formula is this, okay? So it starts from XY. So your X is your independent variable. That is the amount that was spent on the bill, okay? And then the dependent variable will be your Y. That is the amount of tip that was given, all right? So from here, we can easily calculate our S bar by adding all the amount of amount that was spent on food divided by the number of meals. Please, can you add this ones up and then divide by 6 to see whether you get the same figure like I have here, whether you get same 74?
Yeah, 74.
So,
Yes, sir, it's
okay.
74.
Okay, and then what about the Y? The mean is 10? Okay.
It's 10.
Okay, so now the rest is very easy. All that we need to get is, so now see, we need to find the summation of the difference between SI and then S bar, okay? And then when we finish, we come and find a summation between YI and then Y bar. Okay? So let's do it step by step. So we need to find the difference, okay, or the deviation. So for each X value, we deduct the mean from it. So for instance, for S value 34, if you deduct the mean 74 from it, what do you get? You get negative 40. Okay, good. All right. So we do that for all the rest. So you see that if you take value 108 X, that's the value of X minus 74, okay, then that gives you positive 34. You do the same thing for 64. So 64 minus the S bar of 74 gives you negative 10, okay? And then 88 minus 74, okay, gives you 14, okay? 99 minus 74 gives you 25, okay? And then 51 minus 74 gives you negative 23. So you see that we've done Xi minus S bar, okay? So that gives us, so basically this is a difference between each value of X and then the mean of X. Okay, are we okay with this column?
Yes, please.
Okay.
Yeah, that's fine.
Can you calculate the one for YI minus Y bar and give me the figure?
First one minus 5.
The first one is minus 5.
Yes.
Okay, how did you get that?
The value of Y minus the mean of Y.
Okay, right. And then the second one is what?
7.
7, all right. And then the third one,
1.
okay. All right, so you get the concept now. Okay, so for each of them, you deduct the mean from each value of y. Okay, so if we do it for y, then what is left is fairly straightforward. We just remember we are building towards this formula. The difference between, we want to find the summation of this, okay? So we multiply the difference between Si and then S bar and that of Yi and Y bar, okay? And then we find the summation, okay? So once we found the difference, let's multiply the two deviations. That is Si minus S bar and then Yi minus S bar. So minus Y bar, sorry. So for the first row, if you multiply negative 40 by negative 5, it gives you 200, doesn't it? Okay.
Yes.
Okay, and then you do the same for the second row. Okay, so you just multiply. So the second row, multiply 34 by 7. Third row, you multiply negative 10 by 1. Fourth row, you multiply 14 by negative 2. That gives you negative 28. Fifth row, you multiply 25 by 4. And then negative 23 by negative 5. All right? So this gives you the product of the deviations. All right? So when you finish, just sum them. Okay? Just sum them. So that gives you, when you sum them, that gives you the, the numerator. Okay? We are summing the product of Si minus S bar and then Yi minus Y bar. Okay? That's a summation. So that gives you the numerator. Okay? So the numerator here becomes 615. All right? And then remember that this is all divided by the summation of the sum of squares. Okay? So all that we need to do is that for each Si and then S bar, let's find the square of it. So the square is here. Okay? So 200. So for Xi minus S bar was 40. Okay, so if we square it, we get 1,600. Okay, if we square 34, we get 1156. 1,156 or 1156. If we square negative 10, we get 100. If we square 14, we get 196. If we square 25, we get 625. If we square negative 23, we get 529. And then we find the summation of them all. Okay? So the summation of the sum of squares is the denominator. Okay? So here, that is 4,206. Okay? So for us to get B1, the top one, remember, is 615. Okay? That's the summation of the product of the deviations, all divided by the sum of square errors. Okay? That is for the independent variable. That is 4,206. Okay? That's what we calculated here. All right? So when you divide this, B1 gives you 0.1462. Okay? 0.1462. Now, if we go and plug this into the equation, okay, if we want to calculate now we've calculated B1, which gives us 0.1462. We want to calculate B0, okay? And we know that the formula is Y bar minus B1 multiplied by X bar, okay? Okay, just a minute. Yeah. Multiplied by S bar, okay? So since we've calculated B1, which is 0.1462, we can come and plug it in here, the second line, okay? Now we know that Y bar is 10, okay? We calculated this earlier on. So it's 10 minus 0.1462, all right? Okay? And then, so if let's say we want to predict for a food, what do you call it? The S bar is 74, isn't it? So if we put S bar here, that is 74, we get 10.8188. That gives us a B0 of negative 0.818. All right. So we can write the equation like this. Okay. The intercept is negative 0.8188 plus, okay, the B1, which is 0.1462, and then multiply by X. So any value of X that we want to predict, if you plug it in, it will give us the value for the Y. Okay. So let's say somebody spends $100 on their meal. Okay, remember that the X is the amount spent on the meal. If somebody spends, let's say, $100 at the meal, we come and plug the $100 in place of where we have the X. Okay, so when we add everything up, it will give us the value for the tip amount. Okay. Any questions on this one? Any questions? Should I go over somewhere that you missed? Any questions, please?
And please, to the intercept, how you got the intercept?
Okay, so let's go back to the intercept. So you know that the intercept, the formula for the intercept is what we have on the left here. Do you follow that? B0 is equal to Y hat minus B1 X hat, or S bar, sorry. Do you follow that one?
Yes, please.
Okay. And then we had already calculated our B1 to be 0.1462. Is that not
Okay.
it?
Yes, please.
So we just come and plug it in here. So our B1 becomes, so our B0 will be Y bar minus 0.1462 multiplied by S bar, isn't it?
Okay.
Now we know our S bar to be 74, which we've calculated here already.
Yes.
Okay. And then our Y bar is 10. That's the mean of Y, which is also calculated here already. So we just plug in the figures.
All right.
Okay.
All right.
And that results in negative 0.8188.
All right. No.
Yeah.
Thank you.
Okay. Okay. So when we plug in all this, okay, we come to get the equation of 0.8188 plus 0.1462x. So based upon this, we can for every given value of x, we can predict y. We just have to plug in the s value to where we have the x and then calculate everything. So how do we interpret this? For every unit increase in x, okay, for every x, okay, y will increase by, let's say, approximately 15 cents. Okay, y will increase by approximately 15 cents. Okay. So for every S dollar For every $1 the bill amount S increases, we will expect a tip amount to increase by 15 cents. All right. Any questions on simple linear regression before we go on to multiple? Yes. The last, yes.
Yeah, the interpretation is quite confusing.
Okay. So you see that the X here, you see the coefficients here for the B1. So we have 0.1462, okay? Let's say X increases by 1. So let's say X is 1, okay? If we put X as 1, okay, what will the B1, what will, how do you call it? What will, if you, let's say if X is 1, and then you multiply 1 by 1 for 0.1462, what will you get?
0.1462.
So whenever there's an increase, okay, of $1, okay, then Y will also increase by 15 cents. There will be another increase of 15 cents for Y. Okay. You get it now?
Yes, I'm digesting it.
No, don't digest it. I understand it. Let me go over again. Let me go over again. I mean, for every increase, so let's say if Y X increases by 1, okay, we multiply X if the X is equal to 1. As soon as you multiply X, you make X is equal to 1, you have to multiply it by 0.1462, isn't it?
Yes, please.
Yes, that becomes the value for the Y. Is that not it?
Yes.
So for every $1 the bill amount increases, we expect a tip amount to increase by that 15 cents.
No.
Yes.
Please, why are we not considering the minus 0.81, but we are saying it increases by 15 cents?
Okay, so the thing is that when you increase, let's say you increase 0.164, let's say S is now 2. Okay, S is now 2. You see that the remember that the intercept is just a baseline. Okay. So that's just the baseline. So our concentration now is on the variable part, the one that increases. Okay. So remember the baseline doesn't increase. Remember here. Yeah. Okay. No matter the level of X, the baseline stays the same. Have you seen? The first one on your left.
Yes, sir.
All right. No matter the value of X, the baseline stays the same. Okay. So our focus is on the ones that increases or the one that varies. All right. So normally your interpretation will be based on that. Yeah.
Hello, Nana.
Yes.
So I need to go back to where you went there, where the line is, the graph.
This one.
No,
the one I just showed. This one.
No, the graph, the one, yes, this place. So you see, this place, you were saying, you were saying that what was the name? When you are drawing the line, okay, it starts from the B0.
Yes.
Yes. So why wouldn't it be that maybe the new increment, the price would be added to the B0 to get the, I don't know if, so that we are, because at the end of the day we are trying to get the expected price, expected new time. Yes. Wouldn't it be that based on this formula, wouldn't it be that the slope you found plus the base price. Okay.
Yeah, I get what you are saying. I get what you're saying. But the point here is that you see where the B0 is starting.
Yeah.
Okay. Let's say the slope becomes steeper. Okay. It becomes steeper. Let's say instead of here, the slope is going this direction. Can you see my cursor?
Yeah, I can see your cursor.
Okay. Even if it goes to this direction, B0 will still be the same where it is.
Yes.
So that's the main point we are making. So no matter how it varies, the B0 stays the same. So your focus, you say?
Why don't we include that in the?
It is included. It is. So because it's like when you have, put it this way, we are just interpreting we are just interpreting how should I put it? Okay, if you have you are comparing two, if you are comparing two variables, okay, or you are comparing two figures, okay.
Okay.
Well, let's say all of them, one has fixed cost 100, okay, plus variable cost 25, okay. And then another one, fixed cost is 100, and then the variable cost is 20. The fixed cost is the same for each of them, isn't it?
Yeah.
Yeah. So actually, what we'll be comparing will be the variable.
Okay.
Okay. So in the same vein here, if you come and put, let's say x is 3, okay? S is 3, and then you predict the value for y, okay? You add all of them up, you predict the value for y. And another instance, S is 2, you predict the value for y. Don't you notice that the intercept will be the same in both equations?
Yes, please.
So in that case, it will not count, isn't it? If you are comparing the two. So that's why the interpretation, not that we are ignoring the intercept, but just that with the interpretation, we are looking at the one that varies. Okay.
Okay. Okay.
Okay, good. All right. Any other question? Any other question? So basically, you will know that as a data scientist, your model will work this for you, but you should understand how this is done, okay? So that you'll be able to give better interpretation. Okay. So far we've looked at a simple linear regression. So let's move on to multiple linear regression. Any question about a simple linear? Any question about it? Simple linear. It's the same concept we are going to use for the multiple linear regression. With the multiple linear regression here, we don't have just one independent variable. We have so many independent variables. Okay, we have so many independent. So one assumption of multiple regression is that the error term is assumed to be 0. Okay, so we have the intercept, all right, and then we have one independent variable. Okay, that's b1x. We have another independent variable, that's b2s, another independent variable b3s, and so forth. Okay, to whichever level of independent variables that we might have. Okay, so the b0, b1, b2, these are all estimates of the population parameter. Okay, of beta 1, beta 2. You know that. Okay. So, for instance, so a typical multiple regression will have so many independent variables, or more than 2. Okay, 2 or more independent variables. Okay, have two or more independent variables. So here we have one independent variable, that is B1. Okay, so this equation is just an assumption. Okay, so we've not calculated anything. I'm just showing you that a typical multiple regression shows something like this. Okay, so we have the B0, that is the intercept, and then the B1, okay, that relates to X1, okay, and then the B2 relates to the second independent variable, and the B3 relates to the third independent variable. All right, okay, so all these are the coefficients of the variable. Okay, so the only difference between a simple linear regression and multiple linear regression is that here you will have, how do you call it, two or more independent variable. Okay, any questions on multiple linear regression? Okay. So basically, when we talk about the simple linear regression, it is one-to-one. Okay, so you have one dependent variable and one independent variable. Whereas when it comes to multiple linear regression, we have many independent variables that have an influence on one dependent variable. Okay. Any questions on the differences between simple linear regression and then multiple linear regression? Any questions? Yes, Muslim.
Hello, Nana. Does it mean that for multiple regression, when you are drawing the graph, you don't get a straight line? Or...
What do you mean by you don't get a straight line?
You see, for the simple linear regression, the graphs you showed, yours for the intercept and everything, it's a straight line. So is that the same for a multiple regression?
No, a multiple regression can also show a straight line. Okay, they can also show a straight line. Okay, but the interpretation is a bit different. Normally, you take one variable whilst you hold the others constant. Okay, we'll get there very soon. All right. Okay, so let's see a typical multiple regression here and then see how we can interpret this. So let's say X1, independent variable X1 relates to capital investments, okay, in thousands of dollars. Okay, S2 relates to marketing expenditure, okay, in thousands of dollars, all right? And then the Y hat is the predicted sales in thousands of dollars. So in multiple regression, each coefficient is interpreted as the estimated change in Y corresponding to one unique change in a variable when all other variables are held constant. Okay. So in this example, okay, for instance, $9,000 is an estimate of the expected increase in Y, okay, corresponding to 1,000 increase in capital expenditure when marketing expenditure are held constant. Okay. So we'll do a lot more of the interpretations when we also work this using a model. All right. Okay. So for linear multiple regression, there are some assumptions that have to be met. When these assumptions are violated, then you cannot, that means that your data is not suited to be used for multiple regression. Okay? So you might have to use probably a non-parametric way of interpreting your data. Okay. So there is linearity. There needs to be a linear relationship, okay, between the dependent variable and then the independent variable. Okay. There needs to be a linear relationship. So there should be linearity. The dependent variables and the independent variables collectively. So there should be individually and also collectively. Okay. Normally you can see this in a scatter plot when you draw the line of best fits. Okay. Okay. You can see if there is linearity or not. Okay. And then we have what we call the homoscedasticity. Okay. So your data needs to show homoscedasticity, which is where the variance along the line of best fit remains the same or similar as you move along the line. Okay. And then this should be normality, not normality. Okay. So there's normality. So residual errors need to be approximately normally distributed. So your data set should be normally distributed. Basically, that's what you mean. Okay. So we'll have a way of checking that. I will show it to you. Okay. And then there should be independence. Observations should be independent of each other. There should be no issue of collinearity, multicollinearity. So we have issues of multicollinearity when independent variables are related to each other. Okay, when we touch on predictive analytics, I will show you how to deal with issues of multicollinearity. Okay, but as much as possible, you want to remove independent variables that are correlated to each other. Other than that, it will affect your model. Okay, so the regression model that you're going to build, you need to ensure that all the variables are independent of each other. Okay, so let's say you have a model that has, let's say you have, let's say you want to predict the number of people that are traveling on a particular route, okay? And then the model you are using is, the independent variable comprises the amount for the ticket, okay? The amount of fuel that is used, and then the distance traveled, for instance, okay? Now, if within the model you find that, okay, the amount of use, the amount of fuel that is used, and then the distance traveled, okay, if they are correlated to each other, in other words, if the longer the distance, the more the amount of fuel used. Like if you know this, you can know the other. Then there's no need for the two of them to be in the equation. You need to remove one. Okay, you need to remove one of them. So that is where the issues of multicollinearity comes in, where you have independent variables that are correlated to each other, highly correlated to each other. Okay, you need to remove them. Okay, so normally what you do is that you find the correlation, or find the correlation between each of them and then the dependent variable. The one that has the highest relationship, you keep it, and then you remove the one that has the lowest relationship. I don't know whether you follow me. Hello?
Yes, sir.
Now,
Yes, sir.
Okay, so are we okay with these assumptions? We will have a practical look at them very soon. But are we okay with this? Anybody with difficulty in understanding the assumption. So these assumptions don't have to be violated. Okay, so there is the test of linearity. You need to test whether the data is linear. You need to check whether there is homoscedasticity. Okay, you need to check whether there is normality, and then you need to check whether there is independence. Okay, so with the independence, you can use the Watson test, okay, to also check that. Okay, so we'll have a look at all of them. Okay. Any questions? Any questions?
Yes, Nana.
Yes.
Please, with the independence, with what you said, and the correlation thing, I know that you have to remove one, but I wanted to understand the why behind it. If you use the two, what will happen? Why
It
do
will
we
affect your
alter?
model. It will affect your model. So your model, though it will work, it will not give you, there will be, let's say you have so many, this is a case I've just told you about two variables that are related. What about if they are 4 or they are 5? They are all highly correlated. I mean, if you know one, you can know the other. So why keep all of them? So you remove the ones that you don't need. Have you seen? And then keep only one so that your model will perform better. Because one, let's say you have so many highly correlated variables, it's going to affect the time that your model uses to predict, isn't it? Because it has more variables to deal with. All right.
Yeah.
And then the errors that might come, because each of the variables might have its own error and stuff like that. Have you seen? So to prevent all that, what you do is that, remember, you are working with big data and stuff like that. So what you want to do is to remove all issues of multicollinearity, okay? And then just keep one.
Okay.
Basically, that is the foundation for principal component analysis, okay? Where it deals with issues of multicollinearity and then removes it from the model. So when issues of multicollinearity are dealt with, it helps your model, your predictive model, perform better. Okay?
Okay.
Any other question? Any other question? Yes, Muslim.
Yes, Nana. So is it left to our discretion on which one to remove and which one to keep, or there's a rule about it?
Yes, so that's why I'm saying that let's say all these independent variables have an effect on the dependent variable, isn't it?
Yes.
Please, are you following?
Yes.
So the best thing to do is to choose the one that has the most effect on your dependent variable, and then you leave the rest.
Okay.
Okay. When we begin to delve into predictive analytics, there is a way to go about it. We set a threshold. So the ones that does not meet the threshold, they will be automatically removed from the model. Okay.
Okay, thank you.
All right. So any question? Any other question? So we have 4 main assumptions, okay? The assumption of linearity. So we test for linearity, we test for homoscedasticity, we test for normality, and then we test for independence. Okay. So I think probably let us go for our break now. When we come, then we see how we can apply this. Okay, we can apply this test. Okay, so please, when you come, put on your R. Okay, we'll use R to check all this, and then use R also to interpret. So the focus Now you know how to work the regression. How do you interpret a particular model? So we'll take practical examples, okay, and then we see how we can interpret this, and also to look at how these tests are done in R. Okay. So when do we come back? Your break, how long is it for?
So it's 30 minutes.
Okay, so let's come back 35, okay? 3:35 and then thank you.
Yes.
This one?
Yes, sir.
Yeah.
Oh, okay.
Yeah.
Thanks. I wanted to. I was confused as to whether the X also changes or it's just the B1, B2, the coefficients which will change. Thanks.
Oh, but it doesn't even matter if it's sometimes you can get some books that say S1, S2. Yeah, but the X relates to the B2. So if you have S2, it will relate to B2. If you have S3, it will relate to B3 and stuff like that.
Oh, okay. Okay.
Is that okay?
Thank you.
Don't worry about that. Well, we can is test of normality. So we have what we call the QQ plot. Okay. So the QQ plot is what you use in checking whether the data set is normally distributed. Okay. So where you see, so these ones you are seeing here, these are like data points. Okay. So as much as possible, they should fall on this diagonal line. Okay, hey, take your time. All right. Share my screen. Is that Christiana?
Yes, sir.
Yes, that's
okay. Just a minute. Chrissy, I will share, okay? I thought you see. Just a minute. Sorry about that. Please, can you see it now? Is it better?
Please, we can see it now.
Okay. Okay. So we're looking at some of the assumptions. So before you go on to use multiple regression, you should check whether your data is normally distributed. So we call this test of normality. Okay, and one of the plots, I will generate this plot for you. Okay, so one of the plots is what we call the QQ plot. Okay, so you see this diagonal line here. Okay, so the black ones you see, these are like data points, all right? And they should fall on this diagonal line. So if they are very close to the diagonal line, then it means that your data is normally distributed. So here you can see a data, you can see that the data points are, most of them are on the diagonal line. So here you can say that your data point is fairly normal. Okay, so you can go ahead and then use the multiple regression model. Okay, so where you have data points that are scattered all over the place on the QQ plot, then it means that your data is not normally distributed. Okay. So it's one of the points that you need to pick. And then this residual versus fitted values will also, we use this in looking at test of linearity. Okay, test of linearity. We will see all this in R when we go there very soon. So here, where you have data points that are scattered randomly, okay, so you see that they are scattered randomly. You see that where you have the residuals equal to 0, okay, in the horizontal line here, for instance. Okay, so you see the residuals versus the fitted, okay, but the data points are, there is no pattern to the way it is scattered, okay. So for instance, if you have so many of them, okay, like below the residual line or above the residual line, here you can see that they are evenly kind of scattered, okay, or there is no pattern in it, then it tells you that there is the data points are fairly linear, okay. All right, so you can go ahead and use it. But where you see patterns and then they are cluttered to a particular area, let's say to the top or to the bottom, or you can see some patterns in there that tells you that your data that you have is not linear. Okay. So the test of homoscedasticity. So this is where it tells you that you have assumption of constant variance, okay, from the mean. Okay. So this plot, scale location plot, tells you how spread the data is. Okay. So here it is similar to what we did, we checked earlier on, but this one check how spread the data is. Okay. So if it is also not, remember that this one, the difference between this and the other one is that this one is looking at residuals and then fitted values. While this one looks at standardized residuals. So it looks at the square root of the standardized residuals. Okay. So, and then the fitted values. All right. So where this one too is spread like that, okay, it tells you that there is homoscedasticity. All right. But where it is not spread and they are all cluttered to a particular location, then it tells you that the variances are not constant. Okay. So I think I will, yes. So let's see. There's one thing. Okay. So when we go to R, you see another one called Cook's distance. I'll explain that as well. Okay. So, and then we have the test of independence. Okay. So here we can use the Darwin-Waston test. Okay. I'll show you how it is done in R. Okay. So let's go to our R and then see if we can see all of this stuff there. All right. Let's go and take a data set and then we check. We try to develop a multi-regression out of that. Okay. Multi-regression model out of that, and then see if they meet this test of assumptions. Okay. If they do, then we go ahead and then use it accordingly. Okay. So let me go into my R. So I hope you are all within your R Studio ID now. Are we all okay to move? Are we all okay?
Yes.
Okay. So let's go and use one of the inbuilt data sets in R. Okay. It's a popular data set. Okay. So I'm sure you've come across it. So let's import empty cars data set. Okay. So as you know, if the data is inbuilt, normally we use the data command. Okay. Empty cars. Okay, so that's fine. Okay, so when you call it, we should have the data set. Let's view all of it in one go. So this gives us information about brand of cars and some various components of these cars. Okay, so if you want to know more the metadata about this, you can go to help, okay, and then look for empty cars. It will give you the metadata about that. So that's the motor trend car road test. Okay, so the MPG stands for miles per gallon. Okay, CYL is the number of cylinders that the car has. Okay, DSP is the displacement. HP is the gross horsepower. Okay, and then the DRAT is the rear axle ratio. Okay, the sixth column is the weight. Okay, the weight of the car, thousands of pounds. Okay, and then the Q-sec is the quarter mile time, okay, per second. And then the eighth column, you have VS, okay, whether the engine size is V-shaped or straight. So here you have zeros and ones. So if it is 0, that means that the engine size is V-shaped. If it is 1, that means that the engine size is straight. Okay. Then we have AM. This shows whether the car is automatic car or manual. So if the transmission is 0, it means that it's automatic car. So here, if it is 1, that means that it's a manual car, manual transmission. Okay. Now 10 is the gear, the number of forward gears. Okay. So have the number of forward gears, and then the last one is the number of carburetors. Okay, so these are the features of each car. So we have different brands of cars. We have Mazda WAG, we have Datsun. So this an old data set. I don't think we still have Datsun in the system. Okay, so basically we have all this. So this the number of cars that we have. Okay. All right. So let's see if we can create a multiple regression model, okay, based on this. Okay, so let's go back to our main stuff. Okay. So we'll have to manipulate the data a bit. So let's call in our deep learning. Okay. So we are not interested in all the features. Let's pick the few ones that we are interested in. Okay. So with our deep learning, we can select the features that we are interested in. So let's pick miles per gallon, displacement, and then horsepower. Okay. So empty cars, pipe operator. Then we select. So let's select MPG. Let's select displacement. And then let's select horsepower. Let's call this MTC. Okay. That's right. So now when we call MTC, we should just have these three features here. So now we have only we have mass per gallon, we have displacement and horsepower. Okay. So if we want to say predict miles per gallon, that will be used. Okay. Then this becomes our Y, isn't it? It becomes our dependent variable. And then the independent variable will be displacement, and then our horsepower. Okay. Okay. So let's fit our model. So let's fit our linear model. Okay. So here we want to predict miles per gallon. Okay. So let's call this MTC model. Okay. So the function for generating the linear regression model is LM, so linear model. Okay. So the function is LM, linear model. Okay. Remember the equation is y is equal to, and then you have the beta 1, beta 2, beta sub 1, beta sub 2. Remember all those things. Okay. So, or put it this way, y, your dependent variable is equal to your independent variables. Okay. A, B, C, D, and stuff like that. So first of all, our function is a linear model. Okay. So let's put in our equation. What do we want? We want to predict miles per gallon. So that is our y. So that y will come first. So miles per gallon. Okay. And then tilde. Okay. Tilde. So that means that everything on the right, okay, is independent, and then the MPG is dependent upon it. Okay. So our independent variables are displacement, okay, displacement, and then horsepower. Okay, and then we are picking it from our MTC data. Okay, we are picking this from our MTC data. So let's run. Have we all gotten to this level? Are we all on line 13? Let's all get to line 13 and then we can move together. Have we been able to fit your model? You say?
Can you repeat the line 13 again for me? Because I didn't get it.
So the line 13, here we are fitting the linear model, all right? And the function we use is LM, linear model. So this LM stands for linear model, okay? So the linear model into bracket, so into bracket, this is where you have the arguments, okay? So the first argument is the dependent variable. So since we want to predict miles per gallon, is the first one we use. Okay, so this MPG. All right. So MPG, so this tells R that this is your dependent variable. And then you bring your tilde. Everything on the right side of the tilde is your independent variable. All right. So here, our independent variable, we are just selecting displacement and then horsepower. So we are using the displacement of the car and then the horsepower to predict the miles per gallon that will be used. All right. So we are just using this and that to predict this. Is that okay? And then this data argument is that we are picking the data from MTC, which is this. Yeah?
Yes, please. Thank you very much.
Please. All right. Please, are we all on line 13? Are we all okay? Please let me get some feedback so that I don't want to leave anybody behind.
Nana, we are good.
Now we are good.
Okay. All right. So let's plot this model. Okay. So plot MTC model. No, let's run this. Now, when you run this, you see in the console, it tells you hit to see next plot. Okay. So put your cursor here, click, and then press enter. Okay. So the first plot comes. So this is what you have, your residual versus the fitted. Okay. Residual versus the fitted. So this one basically gives you an idea as to the test of linearity. Okay. So you see that the data points, and by default, some of the data points have been identified by the cars. Okay, so if you want to identify all of them by the brand of car, you can do that. Okay, so the data points are evenly spread. Okay, getting to the where the fitted values are larger. Okay, the residual seems to be going up a bit, but they are evenly spread. The main thing about it is that they are evenly spread. Okay, so it gives you an idea as to the linearity of the data. Okay, so they are fairly linear. Okay, where you have pockets, okay, all of them cluttered to one corner or stuff like that, then it tells you that they are not linear. Okay, so this one, they are at random. You see, it could have been better than this. Okay, it could have been better than this, but you can see that they are spread the data points randomly. Some of them are above, so and some of them are below. Okay, so you don't have, let's say, significant number of data points, let's say, being above or below. Okay? So it gives an idea. It is fairly linear. Okay, let's hit the other plot for the second plot. So this gives you the QQ plot. Okay, it is not as we saw in the slides. Okay, so ideally they should all be on the diagonal line. Okay, ideally they should all be on the diagonal line. So but though they are following, you know, on the line, they are not exactly on there. Okay, so this also gives you, remember the QQ plot gives you an indication as to the normality of the data. So this is test of normality. Okay, So the KQ plot gives you the test of normality. So this also, you can argue that the data is normally distributed, okay? Because here they are not scattered all over, okay? Though they are not all of them perfectly on the diagonal line, at least they follow the diagonal line a bit, okay? So you can say that the data is normally distributed, okay? Let's see the other plot. You hit again. This gives us the scale location, okay? So this scale location, remember, is the test of homoscedasticity, okay? So as the other one, as the linearity, this one too, you see that they are spread randomly, okay? So the interpretation here is that they have constant variance, okay? And then the last plot, so this is the Cook's distance, okay? So here we have the residuals and the leverage. It tells you basically, this plot tells you how influential the data points are to the model, okay? So you can see here, normally we are interested in the bottom right corner and then the upper right corner. You see that we have 0.5 Cook distance and then 1 Cook distance to the right. And at the bottom, we have 0.5 Cook distance. And then, so you see at the bottom right, 0.5 Cook distance, and then 1 Cook distance, and then the upper right to 0.5 Cook distance, and then the 1. So if you have data point that is above 1, okay? That is above 1 Cook distance. That means that that data point is very influential. It's an outlier, okay? It's very influential and is far away from the other data points. So here you can see that the data points are all within -2 to 2. Remember, when we're doing, we're looking at when we're looking at z-scores, okay, we said that, and also sampling distribution, we said that about 75% of your data will be within 2 standard deviations, and about 95% of your data will be within 3 standard deviations. All right. So here you see that the majority of your data is within. So here you can basically okay, so you have the negative to the positive. All right. Okay, so they are all within that. So you don't have basically outliers in there. So where you have a particular data point that is, let's say 0.5, that means that that data point is worth investigating, okay? But the rule of thumb is that if you have data point that is more than 1 of the Cook distance, then it has to be removed, okay? So normally when you remove it, you can see that it will have a major effect upon your model, all right? So here there are no outliers in the model since none of them goes beyond the Cook distance, okay? All right. Any questions about the plot? And then let's go ahead and then we can check for the test of independence. That one can be done using the Durbin-Watson test. Okay. So let's see the Durbin-Watson test. Yes, yeah.
No, so please, with the fitted values, the plot, we are just looking at how distributed, whether they are around the 0, some are at the top and some at the bottom, not whether they are biased on any of them. Just as long as there are some data points pointing up above the 0 and some above the below the 0, we take it as a linear.
No, so see, So all of them
Excluding the
have
linear stuff.
all the plots have all the plots have various interpretations, though some of they overlap. Okay, so
Okay.
the residual versus the fitted talks about linearity. This one looks at the linearity. So the linearity. So basically, for a perfectly linear, you see that this line will be on the one that is dotted on the background. Okay, it will be on it, and then you will have, they will be evenly spread. So this one is not perfectly linear. Okay, but it is somewhat linear. Is that okay?
Okay.
And the next one, okay, and the next one is the QQ plot. So the QQ plot look at how normally distributed the data is. Okay. So here, normally you will see that we don't have enough data. See in our slides. Okay, this we have a lot more data. Have you seen? So you see the QQ plot was fairly on the, is much more cleaner than what we have now. Yeah, we have about 16 or so cars, but let's say you have millions of rows. Okay, you are going to have something like this. Okay. All right. So here we don't have enough data, so probably we need to add more data to our stuff. Yeah. And then this one, the scale location. Okay. This one tells us the constants of the variance, that is homoscedasticity. All right. So if they are spread, okay, then there is no, they are not cluttered to one side, then the interpretation is that the assumption of homoscedasticity has not been violated. All right.
Oh, okay. So in this case, you are looking at the spread of the data. Okay.
Yes, here we are looking at the spread of the data. Okay. We are looking at the spread of the data. And then
hello, Nana, please. It seems you're off. Can't hear you. Or am I the only one?
We can't hear him too.
Can't hear him.
Okay.
Hello.
Hello, Felicia.
Please, is the meeting still on? Oh.
Yeah, Felicia, we are on, but it seems Nana fell off.
Oh, okay. I thought it's my network.
No, you're good. I don't know. Probably he's having problem with his network.
Thank you.
Ransford, will you reach out to him in the background to see what is happening?
Yeah, I'm trying to.
Hello?
Hello, Nana.
Okay, sorry. My internet just went off. I don't know how that's right. So let's okay, where did we get to?
Nana, you explained the skill location.
I was explaining the cook distance. Can you hear me?
No, the scale location.
Okay, okay. Okay, so here we're talking about how spread the data is. Okay, so if it is spread like this, then we say that the assumption of homoscedasticity has not been violated. Okay, but where let's say they are all cluttered to the top, let's say above the diagonal line, the horizontal line, or all of them below the horizontal line, then you see that it has been violated. All right. So that is for the scale location. Okay, so it has to be random and then evenly spread, okay, at the bottom and also at the top. All right?
Okay.
Okay, all right. So let's see the test of independence. So probably let me make some comments here. So test of assumptions. So normality. normality, we are looking at the QQ plot. Okay. Linearity. We are looking at pseudo versus the fitted values. Okay. Okay, so the test of independence. Let's look at the Watson test. Watson test. Okay. So let's call it's part of your package. So let's call it from the library. Let's test. So let's do the Watson test on our model. So our model is MTC model, is it? Okay, so all that we are interested here is that where our DW or W Watson, here, this one, where it is greater than 2, it indicates independence. Where it is less than 2, it indicates that variables are not independent, okay? Or where the p-value is less than 0.05, okay? We say that variables are not independent, okay? Or where p-value is more than 0.05, then variables are dependent. Let me just. So where our DW, okay, is greater than 2, okay, where is greater than 2, it indicates independence. Where is less than 2, it indicates no independence. That means that there is multicollinearity, isn't it? Or where the p-value is less than 0.05. We say that it it also indicates independence. So where it is 0.05, variables are not dependent. And then where it is where p-value is greater than 0.05, the variables are independent. So per our calculation, the data set that we have, is it independent or is not independent? Per our calculation and the interpretation that we've given, is does it pass the test of independence?
No.
It's not
Okay.
independent.
All right. Okay. Good. All right. So basically, so these are the assumptions you should be looking out for. Okay. So if you are writing as data scientists, you are developing your model, okay, and then you want to explain to your audience, these are some of the arguments you can bring in for using the particular model that you used. Okay. So if they don't meet these assumptions, then probably use another model, a non-parametric model, okay, to do your tests. Okay. Now, for our purposes, just to let you know how it is done. Okay. So let's assume, for argument's sake, let's assume that they have passed all the assumptions. Okay. So now we go ahead to use the linear regression. Okay. Okay. So let's have a summary of our output. Okay. Assuming they've met all the test assumptions. Okay. So summary of our model, that is MTC. So let's run it. Okay. So when we run this, we see the coefficients here. So this is the intercept. Okay, so this is B0. Okay. Okay. And then this is B1. Okay. And then this is B2. Okay. All right. So here, if you look at where you have three asterisks, that means that they are very significant. Okay. All right. And you can see from the p-values, they are less than 0.05. Okay. All right. Now, one thing you should watch when you build a regression model is to look at the adjusted R-squared. Okay. So this tells you that all the variability in the data set are explained, okay, by the data set that you have. So all the variabilities we are experiencing is within the data set that we have. Okay, so where you have adjusted R-squared, above 70 is good. Okay, mostly you want something between 80 to 100, but above, so 73% is not bad at all. Okay, so this tells you how well your model is doing. So if you do, how do you call it? You generate a regression model and your adjusted R-squared is, let's say, 20%. That means that it's not a good predictive model to use. Okay, so this one, 70% is quite good. Okay, so you can go ahead. So normally that's why you don't use just one model to to one predictive model. You can have several ones, and then you pick them, the one that predicts your data very well. Okay, just one of them. Okay? So we have a look at the adjusted R squared. All right. So if it is above 70, it is quite good. All right. Okay. So basically, that's the interpretation for you. Okay. Any questions on what we've done so far? Yes.
Please, Nana, can you go back again and explain you mentioned that coefficient is the B0, the B1,
Yes.
B2. I didn't really get that
Okay.
part. Can you?
So you can see that this is the intercept. That's the B0. Okay. This is one. This another. This is the coefficient of the other independent variable. That's displacement. Okay. And then the horsepower. Can somebody explain this equation? So this is basically your linear regression equation. Okay. So basically it's y is equal to your intercept, that is 30.7. Okay. Let's use 30.7. So now here, instead of plus, here it is 0. It's negative. So that means your slope is negative. Okay. It's going downwards. So it's going to be minus 0.03 x, okay, x1. Do you get it?
Yes, sir.
Minus 0.02 x2. Okay. So that is this is your equation. Okay.
Okay. Thank you.
So let's make this a comment. So when you work it manually, you will get the same thing, but you will not be able to determine the adjusted R squared and stuff like that. Here, R does it for you, and it tells you how well your model is working. So normally what you do is that practically what you do is that we chose only 2 features, isn't it? We chose only 2 features. Okay. If you go and add other features to it, let's say we had cylinders, displacement, other stuff like weight and stuff like that. Okay, we could add the weight. Let's add the weight and see if our adjusted R squared is what? Put it somewhere, 73%, isn't it? Okay, so let's work it out here and see. I don't want us to lose this. Okay, so let me just copy this whole thing here. Let's add other data set, other features, and see if our adjusted R square might change. And then we can use that. So this time around, let's add weight, okay? All right, so let's make this MC2. Please, are you following? Okay, so let's run this. So this one will be 2. So now we want to add weight to it. So WT. And then we are picking our data from MC2. let's plot. Let's make this 2, model 2. Let's plot our model 2 here. Okay, very good. So this one gives us, okay, so you see that this one is giving us some weird stuff. Okay, so of course this cannot be linear. Okay, all right. This so you see the QQ plot is thrown overboard. Okay, so this one violates the, so you see that we cannot add weight to this particular one. You get it? Okay, it is not linear. Scale location, see how it is. Okay, we can and cook distance. Okay, so you see that let me see, we still have them. Okay, so there are some here that are it's still within the distance, but it doesn't meet the assumption for linearity and normality and stuff like that. So we wouldn't want. All right. Okay. So let's see a summary of, if we are to go ahead, let's see a summary of model 2. So we can't use this because but for some reason the model is doing very well, but we can't, it violates the assumptions. Okay, so we can't. That. Okay, yes, Nancy. Nancy, you want to ask a question? Nancy, your hand is lifted up.
Yeah, Nana, I'm sorry, I missed you in your last few sentences. Yes, Nana, can you hear me?
Yes, I can hear you.
Hello, Nana.
I think there's a delay. I can hear you.
Thank you. Could you please repeat yourself? I lost you. Yeah, I lost you in the last few sentences. If you could just repeat for me, please.
Okay, so what we did was that we came to add weight to the data. Okay. However, when we plotted it, we saw some very weird, output. But for argument's sake, let's assume that all the assumptions were met. Okay. For argument's sake, let's assume that all the assumptions were met. You will see here that when we added the weight, the adjusted R squared is 86%. Have you seen? As compared to the earlier one that was 73%. Do you remember? Okay, so all things being equal, if all the assumptions were met, remember the first one also the assumptions wasn't met, but we assume that they were met, and then just for you to know how the model can be generated. So in a situation where everything is okay, you can choose various how do you call it, features, and then when you finish, you compare the adjusted R squared. Okay, so based upon the adjusted R squared, here you can see that the second one predicts better than the first one. Does it make sense? Okay. This one is 73%. Okay. And this one, the model is doing 86%. Okay. So assuming that all the assumptions were met, they would have chosen the second one. Okay. As a better model than the first one. All right. Yes, Nancy.
Yeah, Nana, please. what we are doing right now, okay, should it follow logic, or should it strictly follow the technicalities of the test and assumptions we are doing?
Okay, what do you mean by should it follow logic?
Like real life logic. For example, excuse me. For example, I understand why MTC, our first model, the summary was giving us those stats. I mean, if you look at a variable like the displacement, I will understand why it would have a negative relationship, a negative influence on, what do we call it? The miles per gallon. Because of course, you would assume the heavier a car is, of course, it would consume more fuel from all the cylinders it is carrying.
Yeah.
Okay, but in then our second model, we are adding weight, which in my opinion should be a really, really good indicator of the miles per gallon. Because of course, if a car is lighter, you would assume that it will consume less fuel per miles it's running, right? But it seems like maybe I am not getting it, but it seems like that is not really the case. So should we rely on the test that we are running to determine how best the model is, or should we apply logic?
Okay, so basically what is happening is that I've realized something I missed in the linear model, but normally we are going by what the data tells us, okay?
Okay.
We go by what the data tells us. So let me see, I think I missed something in the linear model. Let me see. Yeah. So here, so that was the reason why. So here, it should be plus, okay? I think I missed.
Okay, because in the start summary, we couldn't see weight there.
Yeah. So let's run this again. Okay. No wonder we're getting that weird. Okay. So this one too is fairly spread. So
So now the
normally,
plot I was getting was looking more like this.
okay. So normally distributed. Okay. And then also evenly spread. Okay. And then the Cook's distance, none of them is no outlier. Okay, so let's look at the summary again. So I think it was how we fed the model. That's why it was giving us that output.
Okay, no.
So you see that this one is a better model than. So Nancy, to go by your observation, I mean, you see that when we added the weight, so my mistake was
yes,
the model generation. Okay,
it makes sense.
So you see that when we added the weight, the model performed better. So if you have to choose between the two, which one will you choose?
Oh, of course, the second model.
Okay,
it's having a better adjusted R squared.
Okay.
And of course, the variables also in the second model, like it makes sense for them to influence the miles per gallon.
Okay. So you see that.
Thank you very much.
Basically, you're welcome. So basically, the more data you have, the better. Have you seen? The more data you have. However, be careful for multicollinearity. Okay, we will do that. So here, remember that the Ben-Watson test. So let's check the Ben-Watson test for the model 2. Okay. Let's check the Ben-Watson test for model 2. For the independence. Okay, so let's check this. So still less than 2. Okay, so which tells us that some of these data are, there is some multicollinearity in there. Okay, just to give you an idea. All right, so ideally, if this was, though it's giving us a better prediction, okay, we have issues of multicollinearity in there. So in our other how do you call it, when we delve deep into predictive analytics, okay, we will find ways of removing multicollinearity issues in our data set. But you know, is it okay? Are we okay? Okay. Yes, Nancy.
No, please, one more question.
Yes.
You often say that the more data we have, the better.
Yes.
I just want to know, is it the more as in the variables, or the more as in the observations, or the more as in both?
Or when you say observations, each observation will comprise the variables, isn't it? Each observation, let's say you have 1 observation, 2 observation, but 1 observation will have various components.
True.
So the more you have them, the better. Okay, so if you have more observations, the better. And also, okay, I get you. So you are talking about the features too. The more you have them, the better. But
yes,
if you have them and then there is multicollinearity, then do well to remove them. Okay.
Okay, no. Thank you very much.
Okay, so let's move on. Any other question? Any other question? Okay. All right. So good. All right. So let's move on to logistic regression. Let's move on to logistic regression. Once on 2 minutes break. Oh, you're okay. Can we continue?
Yes.
Okay. Yes, Nana.
Now, what we've done so far, we've looked at situations whereby what we are predicting is a numeric variable. Okay. However, you can have situations where what you are predicting is a categorical variable. Okay. So in that case, your normal regression equation wouldn't work. Okay. So simple linear regression uses 1 quantitative variable to predict another. Okay. Multiple regression also does the same. But here, with logistic regression, we will have a situation whereby the dependent variable is a classification. It's a binary variable or a categorical variable. Sometimes you can have yes, no kind of situation. Okay. So in that situation, you cannot use our normal linear regression to predict. All right. So let's see how we can use the logistic regression comes about. Let's start with this example. Okay. So as a first-time buyer, you are busy organizing your financial records so that you can apply for a home mortgage. Okay.
No, please, we are still seeing your R.
Oh, sorry. Can you see my slides now?
No, please.
Okay.
No.
No.
Is it better? Can you see it now?
Yeah, we
Yes,
can all
please.
see.
So I just explained that with logistic regression, you're looking at a situation where you are dealing with a categorical variable, where the dependent variable is a categorical variable. What we've done so far with is a situation where the dependent variable is quantitative or numeric. Okay, So let's see with this example how we can apply logistic regression. Okay, so as a first-time home buyer, you are busy organizing your financial records so that you can apply for a home mortgage. As part of the process, you order a copy of your credit report to check for errors and gauge your credit score, which can range from, let's say, 300 to 350, 850. Lenders will factor in your credit score when deciding to approve or not to approve your mortgage. So it turns out that your score is 720. Okay. While doing your research, you find some online data showing 1,000 applicant credit scores and whether or not application was approved. Okay, yes or no. Okay. So using the data that you found, okay, you develop a model that will provide the probability and the odds of being approved for a given credit score. Okay, discover approximately what credit score is associated with a probability of 50% for being approved. And then you want to input your data into the model to determine the probability and odds of you being approved. Okay, so you know your credit score, you found some data online, okay, and you want to build a model that will determine whether your a typical loan application or mortgage application will be approved or not. Okay, and then you want to factor in your own credit score to see whether you'll be approved. Okay? So when we go into predictive analytics, okay, you will be doing most of this, but here we want to see the mathematical underpinning of logistic regression. Okay, just like we've done for linear regression. So you want to determine how improving your credit score from, let's say, 720 to 750 will affect your probability and odds for being approved for the money. So on my left-hand side, this is the data that you got from online. Okay, data you got. So these are various applications that people have. So people have these credit scores, and then the second column is whether they were approved or not approved. So 0 basically is that they were not approved, the loans were not approved, and then 1 means that they were approved. So this makes it a categorical variable. Okay, please, are we okay with that one?
Yes, Nana.
Yes, Nana.
Now, should you plot this on a scatter plot like we've been doing for regression? This is how it will come out. Okay, it will not, you just have various ones and zeros cluttered together. Okay, so here, basically, you cannot plot a line of best fit. Okay, because the model wouldn't understand. All right, it's not like a normal scatter plots where you have data points everywhere and then you plot your line of best fit across. Here, you just have zeros and ones. So you cannot kindly mute yourself, okay? You cannot basically have a line of best fit in this scenario. Okay, so what happens? So logistic regression, what we seek to do is to model the probability of an event occurring depending on the values of the independent variables. Okay, we want to estimate the probability that an event occurs for a randomly selected observation, okay, versus the probability that it will not occur. All right, and we want to predict the effect of a series of variables on a binary response variable. Okay, and then we want to classify, okay, observations by estimating the probability that an observation in a particular category, such as approved or not approved, okay, such as we have in our problem. So where you have a situation where the response or the dependent variable is a binary situation, yes or no kind of situation, then logistic regression is the best model to use. Okay, so basically what happens here is that the credit score, okay, is normally put into like a black box, okay? Like when you go to the bank, you fill in a form, you want to apply for the loan, they take all the details, and then they enter it into the system. As to what the system does, nobody knows. But they enter your credit score, you enter all your details and everything, including your credit score, into the system. And then the system can determine whether you will be able to pay the loan or not. Okay, do we have some bankers among us? Probably they can attest to what we have some bankers here. Okay, so basically, we input all the credit scores in a model, okay, and then based upon what we feed the model with, it will determine whether a particular application is approved or not approved. So here we are dealing with a mortgage, okay, so loan for buying houses, and this is what the model comes up with, okay? So let's see the mechanics of how this works. First of all, let's understand some terms. When we say odds, odds is the probability of an event occurring divided by the probability of the event not occurring. Okay, so if you have the probability of an event occurring, that is P, okay, then the probability of the event not occurring is 1 minus P. Are we okay with that?
Yes, sir.
Yeah.
Okay, so if you have a fair coin and then you flip the coin, okay, the probability of having heads, okay, the probability of having heads is 1/2, isn't it? And that gives you 50%, okay?
Yes, sir.
Therefore, if you want to calculate the probability of not having heads, is 1 minus 50%, which also gives you 50%. So here the odds is 1, or 1:1. Okay. If you have a fair die, for instance, and you want to calculate the odds of 1 or 2, okay. Remember, a fair die has 6 sides, isn't it? So if you want to,
Yes.
the probability of having 1 or 2, that makes it 2/6. Okay, so 2/6 gives you 1/3. Okay, so the probability of having 1 or 2 is 0.33. All right, so the odds is that the probability of having 1 or 2 is 0.33 divided by the probability of not having 1 or 2. That is 1 minus P. In other words, 1 minus 0.33, which gives you 0.66. All right, so here the odds is calculated to be 1:2, or 50%. Okay, are we okay with this? Okay, so that's the odds. And then we have what we call the odds ratio. The odds ratio. Okay, so let's say we calculated the probability of heads, that gives us 0.5. Okay, and then the probability of the odds of the heads, okay, remember, is 0.5 over 0.5. We calculated it here. Okay, and then we have another issue of loaded coin flip. Okay, so here the probability of heads, we are just assuming that is 7/10. Okay, so if you want to calculate the odds, remember the first one is a separate issue. The first one is dealing with coin. The second one is just dealing with a loaded coin flip. The first one is a fair coin flip. The second one is a loaded coin flip. Okay, these are two different things. Okay, so here the probability of having heads is 7/10, and then the odds in this situation will be 7/10 minus 1 minus 0.7, which is 0.3. So if we want the odds ratio, okay, is the odds of the fair coin and then the odds of the second, okay, which gives us 2.33. So the first one was, and remember the odds 1 over odds 0, you can turn it whichever. Remember, it is just a ratio, so you can do it whichever way. It doesn't really matter. Okay. So the first one, if we are to take odds 1 to be the numerator, then it's going to be the probability of the event occurring divided by the probability of the event not occurring, divided by the odds of the second one. That is the numerator. That is the probability of something occurring, and then the probability of not occurring. Okay. So the odds for the first one is, remember, is this one. The odds 1 is 0.7 over 0.3. That is the first one. That's the first odds. Okay. Or odds 1. And then odds 0, remember, is 0.5 over 0.5. If you work it, it becomes 2.33. So the odds ratio in this situation is 2.33. Okay. Now, we are doing all this because it is going to be relevant down the line. Okay. So do we understand the concept of odds and odds ratio? So we have probabilities, we have odds, and then we have odds ratio. Are we okay with this? Hello?
Yes, Nana.
Okay. Please, I'm not hearing a lot from the ladies today. It's only Nancy that is making contributions. What about the other ladies? I'm not hearing anybody. Are we all okay?
Please, we are paying attention to it. We are okay.
Okay, good, good. All right. So in logistic regression, the odds ratio for a variable represents how the odds change with a unit increase in that variable, or other things being equal. Okay. So let's say we want to check the body weight and sleep apnea. Okay. So weight variable has an odds ratio of 2.25. Okay. So it means that 1 kilo increase in body weight increases the odds of having sleep apnea by 2.25. Basically, that's what it is. And it holds true for any point in the weight spectrum. Okay. Odds can have very large magnitude change. Okay. Whereby even the probability of that thing happening is low. All right. So we will have some practical examples, and then you can see how these things, okay, do work out. Okay. So we have what we call logit. Okay. Now, how does it come about in logistic regression? Okay, remember that the goal of logistic regression is to estimate. Yeah. Is there a question? Okay. So remember that the goal of logistic regression is to estimate P for a given combination of independent variables. Remember, it's the same concept of regression, just that here the dependent variable is a classification situation. Okay, it is not a normal numeric or quantitative variable. Okay, here the dependent variable is a categorical variable. I want to estimate the probability of each of the if situation, whether it will be yes or it will be no. Okay, so to estimate P, okay, we use the P hat. Okay, so to link together a linear combination of variables, okay, to the binomial distribution, that is the yes-no scenario. Okay, we use a function called logit. So the logit is what maps the linear combination of values. Okay. All right. So here it links them up, and then it puts them between the values of 0 and then 1. Okay. Remember that probability is also between 0 and 1. So what the logic does is that it helps us to be able to calculate the probability, okay, of an event occurring or not occurring. All right. Okay, so when we find the natural log, okay, of odds, okay, is the same as the logit. Okay, so when you have the logit P, okay, it's the same as taking a natural log of P over 1 minus P. You just follow through this, and then we'll get to the latter part. You see that it's very easy to follow. Okay, so here we find a natural log of P over 1 minus P. Okay, so that is the logit. So when you find a logit, here you see that the line crosses 0.5, okay, on the x-axis, okay? Remember, the x-axis is between where the line crosses at 0.5 is between 0 and 1. Please, can you see it? Between 0 and 1. So all that we are doing here is that we are using probability scale and then comparing it on, we are creating like a logarithm, okay? So a logarithm axis, all right? And then we map that to a probability scale. So here we can see that between 0 and 1, okay, the probability is 0.5 when the logit is 0, okay? The probability is 0.5 when the logit is 0. Now, we can turn this the other way around. What we want to do is for the probability to come to the y-axis. So let's say we turn, in your mind, see that we turn this table, okay, where the s-axis now become the y-axis, and then the y-axis become the x-axis. In other words, the probabilities come to the y-axis, okay, and then the logarithms comes to the x-axis. So the one currently, what we have now, the s-axis basically is the probability, okay, and then the y is the logarithm scale. But we want to turn it whereby the y becomes the what do you call it? The probability, and then the x becomes the logarithm scale. Is that okay? Right. So when we do that, then the logit, we find the inverse of the logit, okay? And that is equal to 1 over 1 plus Euler raised to the power negative a, which equates to Euler raised to the power alpha over 1 plus e, okay, or Euler raised to the power alpha. Don't be scared about this. Euler is just a constant, okay? Normally you see that on your calculator. You see an E on your calculator. If you have a calculator, you can check it now. It's a constant, okay? So what this does is that when we turn it the other way around, okay, it becomes Euler. So when you find the inverse of this, okay, it becomes Euler raised to the power alpha over 1 plus Euler raised to the power alpha. Okay, so now you see that the probability, okay, the probability values has become the y-axis, and then the logarithm scale has become the x-axis. Okay, so now it has turned from what we had here, okay, to a situation where we have like an x. Okay, so this is what we call the sigmoid curve. Okay, so this is what we call the sigmoid curve. So in terms of probability on the y-axis, is between 0 and 1. Okay, so if you see on the logarithm scale, where you have logarithm values that are negative towards the negative, you see that the probability is low. Okay, so where logarithm is -2, you see that probability is about 0.1. Where logarithm is -4, probability is like 0 point something, very, very small. But where the logarithm take on positive values to your right, you see that the probabilities begin to increase. Okay, so when you get to let's say, logarithm scales number 6, for instance, probability is very close to 1. All right. So all of them is between 0 and 1. So this is what we call a sigmoid curve. So based upon this, it's able to link. Okay. So now, based upon the earlier FICO score that we had, okay, using the sigmoid square, the sigmoid score, the sigmoid curve, sorry, and then the logit, we are able to link the approvals and then the non-approvals. Remember, they were between 0 and 1. Okay, so by using the Euler, okay, over 1 plus Euler raised to the power alpha, okay, the sigmoid curve has been able to link the approvals with the non-approvals. So here you can see that as the FICO score reduces to the left, okay, the probability of being approved reduces, okay, it reduces, okay, and then when the FICO score goes to the right, let's say from 600 going, you see that the probability increases to towards 1, okay? Please, does it make sense? Is it okay?
Yes, and it makes sense.
Okay. So now the beauty here is that this logic that we are talking about, okay, the inverse of it, for instance, the Euler, okay, the inverse of P minus 1 over P is the same as the beta. Remember the regression equation, okay? So the alpha that we have here, the alpha that is on top of the Euler is actually a regression equation. So it's Euler raised to the power regression equation, okay, over 1 plus Euler raised to the power of the regression equation, okay? So all that you need to do is to calculate the regression equation, and then you put it into the Euler, okay? So the probability of determining whether an event occurs or not occurs is the last one. The probability here is equal to Euler raised to the power of the regression equation. So if it's a multiple regression, you are going to have B1, B2, B3, and so forth. It doesn't matter, okay? So this one will be in terms of logistic regression, all right? So here we have Euler raised to the power B1, that's the B0, that's the intercept, plus the slope of B1, all divided by 1 plus B1, B intercept, and then this, okay? So this is the estimated logistic regression formula, so for determining the probability. So upon all that we have done, we've come to this. So it's just simple. If you want to determine the probability of a logistic regression, it's just the Euler raised to the power of the regression equation, all right? Divided by 1 plus Euler raised to the power of the regression equation. That's all. Okay? So let's put this into context. So based upon what, if around this, okay, in SPSS, you realize that just look at the interpretations, that's all. So on your left, you see that the probability is equal to Euler raised to the power of the regression equation, isn't it? Divided by 1 plus Euler raised to the power of the regression equation. Now, if based upon the information that you have, okay, the FICO score that was collected, okay, this one, okay, we can run a normal regression, okay, and this is the equation that comes up. So we have the intercept or the constant, and then we have the slope for the FICO score. Then you go and plug this into the formula, okay? So you have the probability. So you have the Euler. Remember, the Euler is a constant. So Euler raised to the power of the intercept, okay, plus the coefficient of the FICO score, okay? And then you have your X1, all right? And it's the same thing here. So now that we know our FICO score to be 720, we can plug that one in. Okay, so when you plug that one in, you are able to calculate the probability. So therefore, if we have a FICO score of 720, the probability of we being approved is about 77%. Any question? Should I go over something? I missed something. Any question? So just bear in mind that when it comes to logistic regression, we are looking at the probability because of the fact that it is a categorical variable. We cannot use our normal regression to do it. So we calculate the probability of an event occurring or not occurring. And then probability is given by Euler raised to the power of the regression equation, okay? Divided by 1 plus Euler raised to the power of the regression equation. And then if you want to calculate the probability of a particular variable, you plug it in. So this time, our credit score was 720. Okay, so we plug it in, and then we are able to calculate the probability. Okay. All right, so let's go back to our R. Let me show you something. Then we'll come back to this. Okay, let's do a logistic regression with our R. Okay, we'll come back to this. So we still have our empty cars. Logistic regression. Please, are you following what we are doing so far? Are we okay?
Yes. Yes.
Okay. So let's create a logistic regression model. Okay. So normally we use a function general linear model. Okay. And then formula. The argument is a bit different. So here we are still using the empty cars. Okay. We want to use the empty cars. Okay, so here we want to remember the empty cars. Let's go to help. When I explained the AM was either manual or transmission, okay? Either manual or transmission, okay? So we want to predict whether a car is manual or automatic based upon the weight. Okay, so per the data that we want to predict whether a car will be manual or automatic based upon the weight. Okay, so since the dependent variable here is categorical, that is manual or automatic, that means that we cannot use normal regression to do. We have to use logistic regression. Is that not so? Okay.
Yes, Mama.
All right. So let's put that in the formula. So here we want the AM. Remember the AM is the name of the. Do we have? Okay. So we use empty cars. So AM is the dependent variable tilde weight. Okay. Okay. So our data, let's pick it from the empty cars that we have. Okay. And then this is what Miss R understand that you want to do, how do you call it? Logistic regression. So this binomial. Family is binomial. So let's name this. One independent variable dot GLM. The same as what you have in the slide, so that's yeah. Okay, let's run this. So let's see the summary. So we are really interested in this. Okay. This one, the estimates. Okay. So this is the intercept. Okay. And this is the coefficient for the weight variable. Okay. Can somebody interpret this? Yes, Nancy.
And I'm just giving a try.
Oh, just give it a
I
try.
am thinking there's a negative relationship here. So
Okay.
the heavier a car is, the lower the chances of it being. No. Let me come back later.
Okay. Okay, come back later. Okay. Anybody wants to give a try? Okay. So probably it's based upon what we are doing, since we want to link this to whether a car is, remember that probably it's not a fair question because the dependent variable here is not a numerical variable, it's a categorical variable. Okay, so probably let's calculate the probability, and then when we are done, you'll be able to understand this better. Okay, but good work for the try anyway. So once we have this, let's go back to our slide. So be mindful of this. So you see that the intercept is 12, isn't it? And then the weight is negative 4.02. Okay. So if we go to the slides, we have same thing here. Okay. Okay, so we have this estimate here. All right. So that's all that we are interested in for now. Okay. So we know, so our estimate is still here. So we know that the probability, okay, for the logistic regression, okay, is Euler raised to the power the regression equation over 1 plus Euler raised to the power regression equation. So once we know the estimate, we come and plug that in. Okay, so we have the probability is equal to Euler, okay, the intercept that is 12.0.4, okay, minus the coefficient of the weight to be negative 4.024. Please, are you following?
Yes, sir.
Okay, so
Yes,
we are just plugging what we've calculated. Okay, the model gave us. We are just plugging it in here. Okay, so based upon this, please calculate the probability. Where if we have, once we have, so this is our model now. So I want you to predict the probability of a car being automatic or manual if the weight is 3.2.17. Kindly work it out and let's see. Work it out, man. I have not worked it out here. I want you to do it based upon what we've done already. So those with calculators, you see the Euler, or if you are using your phone, use the scientific calculator. You see the Euler is a constant, and then you plug in your regression equation, and then we have your x. You have your x. So your x here will be 3.217. Okay. So calculate the probability.
Nana, please, for which of the weights? The first one?
The first one, we do the first one, then we do the second one. Okay. So calculate the probability. When you are done, calculate the odds as well. Yes, anyone?
The first one, 3.217.
The probability. Okay. So yeah, 3.21 there. Also, what is the probability?
0.2879.
0.2879. Okay. So let's write this somewhere. What was the weight? 3.2 what?
17.
3.217. And then the probability was what?
0.2879.
0.2879. Okay, did you all get the same thing?
Yes, no, 0.2879 is
0.2879. Okay. So we wanted to to predict that a car is automatic, okay? Automatic, or it is manual. Remember that we want a situation whereby we want the the relationship, okay, was whether the car was so this is what I wanted to get at. The AM. The AM stands for the transmission, isn't it? Hello? The AM.
Yes.
Remember that we made the AM till that weight. Okay? So based upon that, now we are able to predict the probability that the car is automatic, or so here is giving us 28%. Okay, so therefore, so the weight of the car, which is 3.217, okay, is giving us a probability of 28%. So let's say if the 28% of becoming the car being automatic is 28%, then the probability of the car not being automatic is 62%, isn't it? Do you get me?
Yes.
Yes, sir.
Okay. So in that case,
did you say 62%?
yes, so 28 plus 62, isn't it? Or is it 72?
72, yes.
Sorry, 72.
72.
Okay. 72. So normally when we get into predictive analytics, you understand this even more, in the sense that it takes the one. So if the threshold is less than 50, it will discard that. So if, let's say, in a situation here where the threshold is the probability is 28%. Okay, let's say the 28% is for automatic cars. Okay, the probability of getting automatic car is 28%. Then, or let me relate it to the FICO score. I think it makes more sense. Then I'll bring it back here. So let's say if we work out the probability, and the probability of, let's say you apply for the loan and the probability of you paying back is 28%, then you'll be rejected. Okay. Or if your probability of you paying the loan is 78%, then you'll be approved. Okay. In the same vein, if we bring it here, the probability of, if the probability of getting an AM, automatic car is 28%, okay, then it will not be predicted as the car being automatic. It will be predicted as the car being manual. All right. So it calculates the probability for the event happening and the probability of the event not happening. Then to pick the larger one, the larger probability, and use that to classify. Let's say we want to predict whether a car is automatic or is not automatic. Okay. Now, if we were predicting that the car is automatic, and then we calculate, and then the probability is 28%, the model will predict that the car is not automatic, because the probability that we calculated for automatic is 28%. Okay. Therefore, the probability of it being manual car is 72%. Does it make sense? Therefore, because 72% is bigger than 28%, it will classify that as, as an automatic car. Should I come again? Hello?
Yes, please.
Yes, please.
So all that we are doing here now is just to calculate the probability, but I wanted to go a step further. Okay. So, but are we okay with the probability?
Yes.
Let's start from here. Are we okay with the probability? So now the probability of the car being automatic or manual is 28%. Is that not it?
Yes,
Oh, we need to
but that
calculate
is
it.
for the weight of, yes,
So
but
for a
that is
weight
for the
of
weight of
3.2.
0.217.
Okay, so what about the odds? Did you calculate the odds? What about the odds? Remember that it is P divided by 1 minus P. So if we know P, we can have the denominator and then we calculate the odds. It's going to be 28 over 0.28 over 0.72, isn't it? Hello.
Yes.
Yes, sir. Yes, sir.
Okay, so what is the odds?
Zero 0.38.
0.38. All right. So calculate the probability for a situation where the weight of the car is 3.317. I think I better stay around here so that you go into place with the probability. I was trying to go a bit ahead of myself. So let's understand this and then we can build up. Okay. What did you get for where the weight is 3 point?
It's 0.212.
213.
0.213. Okay. So by using the logic, okay, we've been able to calculate the probability of a categorical variable happening or not happening. Okay. So basically, where you have a situation where you have a categorical variable and they want to predict, okay, we use the probabilities to determine whether it will happen or it will not happen. Okay, we use logistic regression. Okay, we use logistic regression because where you have categorical variables like zeros and ones, you cannot use your normal scatter plot. Okay, so we use the logic. Okay, and then we follow through the calculation and establish that it is the same as the Euler raised to the power of the regression equation divided by 1 plus Euler raised to the power of the regression equation. So once you are able to work out the estimate for the intercept and also for the coefficients of the other independent variables, it doesn't matter whether it's a single variable or it is multiple regression situation. You just come and plug them in here, okay? And then you'll be able to calculate the probability of the categorical variable happening or not happening. And once you've calculated the probability, you can also calculate the odds of that event. Okay. Any questions? Any questions? Yes, mostly.
Nana, please, could you please go over the odds again?
Okay, so the odds, like as we have here, basically is so the odds is P over 1 minus P. Okay, so we calculated the probability, the first one to be 0.28 for the P. Okay, so the odds will be 1 minus P, that is 0.72. If you add the top and the down, they should give you 100%, isn't it? So that is what gives you the odds. All right.
So Nana, you are not going to divide it.
I'm not going to divide what?
The formula is P divided by, or is it over, is over,
Yes,
So when we are
division.
doing the calculation, let's say with the example we are using, when we got the 0.289 as the P, so
Yes.
1 minus the P is 0.711. So
Exactly.
you are not going to finish
So
the
you divide.
calculation.
So it's going to be 0.28 divided by 0.72.
Okay, you
That
get
was what will give you the odds.
0.406.
Yes, that was what will give
So
you the
what
odds.
is the interpretation?
So here, what this means is that the odds of, let's say here in a situation here where we have the odds of having 1 or 2, okay, is 2:1. Okay, so that means that the odds of not the situation not happening is much more than the situation happening. Okay,
Oh, okay.
so if let's say the 78%, the 72% that we calculated for, remember when we calculated the probability, it was 28%. Okay. So let's say the 28% is for the car being automatic. Okay. And then the other one is for the car not being automatic. So if you calculate the odds, okay, you got 0.4 something. What did you get?
0.406.
So that means that the odds of a car not being automatic will be the 0.4 thing that you've calculated. So the odds is more than, you know, the thing being how do you call it? The reason why I'm finding it a bit difficult here is that we've not established that the car, the AM, you remember that 1 is for automatic, 2 is for manual, or 0 is for manual, all right? Per the metadata that we have in R, okay? So let's assume that 28% is for the car not being automatic, okay? So it means that it has a very low probability. That means that the probability of the car being automatic is 72%. You get that one?
Yes.
So if you are finding the odds between automatic and then the manual, you see that the manual is bigger than the one for the automatic. So that is the odds. Yes.
Thank you.
Okay. Please, any other question? Any other question? So at least now we know the mechanics of both linear regression and then logistic regression. Okay. This is just how it is developed and then derived. Okay. In our other courses, we see how we can apply this in our classification models. Okay. Yes. Yeah.
So Nana, please kindly correct me with this particular where you are, the slide that you just went on.
Which one?
Wait, the R.
Yes. Do you want me to go
we
to R?
used no on the slide.
Okay. Which one? This one?
One step back. Yes, sir. So we use the weights to determine the transmission, and that gave us this intercept and the weight variable here. And then we went to use these particular values to calculate the probability and the odds. So how I understood it was we're trying to figure out how the weights will help us to predict whether a car is a manual or automatic. So
Yes.
with the calculations that we've done earlier on, if we are calculating a weight of 3.217, the probability of determining that particular car is either automatic is what we just calculated. Is that what we are trying to do?
Yes.
Oh, okay.
Remember that with classifications, with classification models, we'll get into it when we do predictive analytics. With classification models, once once we get our data, we train the data, okay? And once we train the data, we can use the trained data to do predictions, okay? So if you have a situation where we are dealing with categorical variables, like want to predict, like the example we just did, we want to predict whether a loan application will be approved or not approved, okay? It uses this logistic regression to do that, okay? And then when it calculates it and then the probability is low, let's say you apply for, based upon your credit score, blah, 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 we've calculated, and then your probability is low, it will reject the loan. If your probability is high, it will approve the loan. So here, if the probability, you know, for predicting that the car is automatic, okay, is high, then it will predict the car as being automatic. If the probability for the car being automatic is low, then it will predict the car as being manual. Okay.
Okay.
All right.
Thank you, sir.
Any questions? Any other questions? Okay, Muslim.
Okay, Nana, I wanted to ask, per the formula on the screen right now, if we were having multiple independent variables, and we were to find out the probability,
it's the same thing.
Going to be given like, we would have to be given like two variables, like two values to be able to check the probability. Is that not the case?
No, so if we, let's say we had 3 independent variables, okay? Then our estimates here will, let's say we have horsepower and also we have like the one we did for earlier. Let's say we want to find out the impact of horsepower and also, let's say, miles per gallon upon whether the car is manual or not manual. That means we are going to have 3 estimates here, isn't it?
Yes.
So apart, so you come and plug all of them here. So you will have the intercept to be 12.04 minus 0.02 for the first independent variable, plus the second independent variable, plus the coefficients of the third independent variable. Have you seen?
Yes.
Just like you have for your normal multiple regression, and then you calculate the probability.
So I'm saying, in order to calculate the probability, are we going to be given, like, for example, what you've done right now, weight equals 3.217. The others are also going to be given. Is that not so?
Oh, yes. That's
what I want to ask.
Oh, okay. I get you. Okay, yes, of course. Because that's all you are going to use to predict, isn't it?
Yeah. Thank you very much.
Yes, Francis, please go ahead.
Yeah, Nana, the examples we've taken so far, our outcomes are mainly to either yes or no, or automatic or manual. What
Francis, I think I can't hear you. Your line is not clear. Can you come again? Am I the only one?
You can't hear him too.
Yes, we can hear you. So, Francis, kindly check your...
He's a robot.
Okay. Francis will have to come again. Please, any other question?
Nana, I think what he wanted to find out was, why are we doing with only like values that take 1 or 0?
Yes, because those are the classifications. When we talk about classifications or categorical variables, okay, you have, it's either this or that, okay? But they are not numeric, okay? So sometimes you will deal with situations whereby you want to classify whether if it is a loan application, whether it will be accepted or to be rejected, or if you are checking on something, it is a yes/no scenario, and then you want to predict whether it will be yes or it will be no, we use logistic regression. Okay?
Okay.
So it gives you kind of options. You are not limited to only quantitative variables which you can use to predict. That means you can also predict qualitative variables, have you seen? Or qualitative outcomes, okay, where the outcomes are categorical, you can predict, okay, based upon using logistic regression. Okay. All right. So I think yesterday I wasn't able to meet you. I wasn't well. So please, can we schedule a time for an evening session, and then we will do test of independence, Chi tests, and then I'll give you the assignment as well. Tuesday, Wednesday, or you get back to me and let me know the day that suits you. Or you want us to decide here, and then we can know how to plan the week.
Now, please, when are your available times?
No, you let me know your time so that I work my time around yours. Okay.
Okay, Nana. So I think give us time to think, and maybe by the end of today or tomorrow morning.
Okay, so let me know by the end of today, okay, so that I can plan my time.
All right, sure.
Okay, so we discuss the other one, and then I will give you the assignment.
All right.
Okay. Please, are we okay? I'll be here for the next 5 minutes. So if you want any question, you can still ask, but we are done for today. Thank you very much for your time. Okay, and have a lovely evening. Okay. So I'm still here. Anybody wants to ask a question, please do so.
Nana, this one, when we were doing the R, when I was using the LM test, after calling the library and I type in the LM dots, I saw some fits, but we didn't use that option. We've not gotten there yet, right? Oh.
Which one? Let me see. Let me stop this and then go to. Yeah, which one? Wait.
Yeah, when you type in the LM.
The linear model.
Yeah, the linear
this
model.
One. Yeah, this one.
Yes.
Mm-hmm.
Yes. When I was following, I typed in LM and I brought a dot and it brought some fits. So I thought we were going to use that option to put in the data.
Like
LM that's a different thing.
Oh, that's a different thing. Okay.
Yes.
That's a different thing altogether.
Oh, okay. Okay.
All right. Okay.
And a last question before we go. This Muslim,
Yes.
about the categorical values, that means it can be more than just 2, right?
No, categorical variables are just 2.
Oh, okay.
Okay, so it can be more than 2, but here we are looking at binomial. Okay.
Oh, okay. So the logic is strictly for binomial.
Yes.
Oh,
so as for categorical variables, you can have 3 or 4, it depends. Okay.
All right.
But here we are looking at binomial distribution. Okay.
Okay. Thank you.
Hello, Nana.
Yes.
Please kindly make available the recording on time for us, because today's class is very loaded.
I'm not the one recorded though. I'm not the one who recorded.
Oh, okay.
So please put pressure on the police who recorded.
The recording.
But why
Network there
didn't
is
you
fast.
record? You didn't record and you are putting pressure on somebody to bring it in.
So, but you said you only allowed 2 people to record. So once the recording is set.
Okay. But it seems to be only one person recorded, or
I
no
didn't
problem,
really.
no problem. It's a lot to take in today, isn't it?
Yeah, yes, sir. We quickly need to go over it, or else it become
Yes,
a
yeah.
big
So,
issue.
and that's the mark of a data scientist. Okay, so now you are getting into it proper. Okay, all right. So, yes, have a wonderful evening and speak to you soon. So let me know the feedback, okay, as to when you want us to meet. Then we can do our last topic and then discuss the assignments. Okay.
Okay, Nana. Thank you very much.
Okay.
Take care. Take care. Bye. Bye.
You too. Take care.
But I just passed by.
That didn't have a phone. I'm watching here. Wi-Fi media. Wahala. Fee, be 2-3 weeks ni. Kasembwa. Then I do 2 o'clock. And then last week. Now I'm in Tete. Mom. What down for? Brother, born me be shadi for fridge no. Sorry, no, sorry.